Here we're going to put everything together. Let's just remind you that R stands for resistor. We saw that for the RL circuit. L stands for inductor. C stands for capacitor. We saw that with the LC circuit. Okay? Now, obviously, if I have a resistor, I have an inductor, I have a capacitor, each of these circuit elements is going to play a different role. Okay, let's just take a guess what's going to happen here. I remember with the LC circuit that it was very similar to the simple harmonic oscillator. Okay, it's very similar to a spring with a mass attached to the bottom of it. Okay, now in the LC circuit, that thing would oscillate forever because we saw that the solution was that the charge on the capacitor as a function of time was equal to some amplitude times the cosine omega t. Okay? Now, in the case of the resistor, we saw that the resistor would restrict the flow of energy. But it also has another purpose here. A resistor will also turn some of the energy from electrical energy into heat. Okay? So what we're going to see here is the RLC circuit is a nice electrical analog, not for the simple harmonic oscillator, but rather for the damped harmonic oscillator. Okay? That basically it will still oscillate up and down, exchanging energy between the capacitor and the inductor. But this time, the oscillations are going to eventually die out as the resistor turns some of the energy into heat. Okay, so let's take a look at this. We have our RLC circuit. In this case, again, we haven't included any voltage source. We're going to assume that our capacitor is going to start as a charged system, and it's going to initially have the energy. Okay? So as we close the switch right here, what is going to happen? Well, the current is going to flow from the capacitor to the inductor. Charge is going to go through the resistor, and then it's going to change the polarity of the capacitor just like it did for the LC circuit. Okay? But we've got this guy right here. What is that going to do? Well, we know that the power that the resistor converts from electrical energy into heat, or really from electrical power to thermal power, is going to be equal to the current that flows through it times the voltage across it, which is also equal to I squared R. Okay? So basically, when it first starts running, it's going to give off a lot of power, but as it oscillates back and forth, the power loss is going to become exponentially less, and this is going to lead to an exponential decay. So again, the capacitor is initially charged, the switch is then closed, and the oscillation begins, but now we have this little damping effect from the resistor where it's going to bleed energy out into the environment. Okay, let's go back to what we did before. Earlier, we came up with an equation for our LC circuit, and so it was very, very similar to our simple harmonic oscillator. Okay, here we use, oh, come on. Here we use Kirchhoff's rule for a loop. If we go all the way around the loop, right, we go from the inductor to the resistor to the capacitor. the total voltage change has to be equal to 0. And just like we had before, here is my contribution from the inductor. Here is my contribution from the capacitor. But now I'm going to apply Ohm's law to the resistor. And I know that V equals IR. I is dQ dt, right? Current is the change in charge divided by time. And it's still times R. So that's going to create an extra term in our differential equation. Okay, so what we had previously, what we had for the previous case, for the simple harmonic oscillator, is we had this term right here from the inductor, this term right here from the capacitor, and it was a second order differential equation. And we also said it was homogeneous, which are terms that unless you've taken differential equations, you probably are not familiar with. But now we've added a damping term, okay? And we did this for the damped simple harmonic oscillator, and that gives us a slightly different solution than we got before, okay? What that does is it still gives us this amplitude, right? Still gives us this amplitude Q0 for the charge. We still get this oscillation cosine omega 0t, but the resistance also has this extra term right here. And notice that this alpha depends on the resistance and also depends on the inductance, okay? Makes sense why it depends on the resistance, but the larger the inductor is, the more it's going to slow the current down or take longer for the current to dissipate. And that's why it delays the exponential decay, all right? Same thing goes with the current. The current is the second derivative of charge as a function of time. So now we get this new term right here, okay? Just like the damped harmonic oscillator, we actually get a slight shift in the resonant frequency. It's not 1 over the square root of LC. There's also this extra term right here, but it's pretty close to 1 over the square root of LC. Okay, so if I charge my capacitor, I then close the switch, I am going to get something that looks like this. And that's just our underdamped simple harmonic oscillator. Okay, that's all it is. So again, what's really nice is that we can see that what we learned in physics 1 with the simple harmonic oscillator actually has an electric analogy in the RLC circuit. So that's really, nice to see, comforting to see that we learned something, but we can apply it in other situations. Okay, so again, the RLC circuit is an analog of this damped harmonic oscillator. There is our resonant frequency, and probably the nicest application of this is the simple radio. Okay, now with radios today, they all have this digital tuning, and they're much fancier than what I'm showing right here. But basically, here's how the old radios worked, and this is going back even to the oldest of the AM radios. Probably it would be more analogous here is the old wireless telegraph. But in any case, we have here the listener is going to basically use the voltage of the oscillation to to hear the electric signal turned into sound. But we have the antenna, which is coupled to our inductor. So that's going to introduce energy in the form of electromagnetic waves, which will produce our magnetic field, right? And then that's going to oscillate back and forth and exchange energy with the capacitors as they charge and discharge. Well, here's the thing. We see that roughly to an approximation, the resonant frequency for the circuit is equal to 1 over the square root of LC, okay? I've eliminated the resistor here, but there is some resistance here. So that's going to shift that just a little bit, okay? So we have this one capacitor C2, but we are going to add to that this capacitor C1. If we remember from our capacitors, the equivalent capacitors for capacitors in series are the first capacitor plus the second capacitor. So this right here, the C1, is actually a variable capacitor, okay? C2 gets you in the general region of where you want to tune, right? So let's say that we're tuning in the AM band, okay? That goes from, like 500 megahertz, 500 kilohertz up to like 1.5 megahertz. Okay, so this would sort of get you in that ballpark. This C1 would then be a variable capacitor, which would be much smaller than C2, but allow us to tune between different stations. So that's basically the whole principle behind here. We think about, okay, all frequencies are coming into this antenna, right? But only the frequencies that match the resonant frequency of the radio of the RLC circuit are the ones that are going to produce an oscillation, okay? So it basically has a resonance which will only allow it to oscillate at the tuned frequency. So that is the basis for the radio. And obviously, with today's radio, there are different ways of encoding the information. Either through amplitude modulation and frequency modulation. On top of that, it's digitized. So you would actually have a digital to analog converter before you'd actually listen to it. But not much has changed for the main part of the circuit, which is the resonator for the radio. Still an RLC circuit.